All right. Good morning, everyone. So today, or I should say, the last couple lectures, we've looked at logistic regression, and this is a form of what we call classification. So when you're doing regression on a dummy or categorical variable, and you are looking at essentially classifying specific outcomes. And so what we'll do today at the beginning of class is to look at a couple other examples besides logistic regression for classification, so that you'll have a couple more tools in your tool belt, and then we'll move on in the latter half of class to talk about starting to move beyond linear models. Okay, so other classification examples. So the first one we're going to talk about is called linear discriminant analysis, or LDA. Probably not as commonly taught, but I guess what I'll talk about are some rough guidelines for considering this type of model. So this is better for well-separated classes. In other words, if your response variable is sort of well-boundaried, a linear discriminant analysis can do a better job than logistic regression at prediction. If predictors are normally distributed, more than this approach is more stable than logistic regression. And so this is partly, this is one of the reasons why it's always good to do some exploratory analysis on your data, because it helps you figure out what are the best sorts of models to be using. So, if you are trying to create a model to do classification, right? So if your response variable is like a dummy or categorical, I think one of the things to look at is the distribution of each of your explanatory variables. And if you happen to have a lot of normally distributed data, which isn't always the case, right? Then an LDA may suit your purposes better. Okay, wait, I see a comment. Is it just me, or I can't hear you? I did get a little... Okay, give me 1 second. I did get a notification that my internet is not super stable. Okay, people are saying they can hear me now, but let me check something really quick. I will be right back. Okay. If folks are having trouble, actually what I'm going to do is I'm going to turn my video off. If folks are still having trouble hearing me, please let me know, and I will switch the audio device to my iPad. Okay. Where was I? Okay, so I'll just reiterate my last point, which is that look at your data, look at your explanatory variables, and if the distribution of the data is normally distributed, then it may be a good idea to use an LDA as opposed to logistic regression. And it won't always be the case that your data is normally distributed. So and then oftentimes, this is popular when more than 2 response classes. Although I wouldn't say this is in and of itself a reason to use LDA. I think it'll depend on the context of other contexts related to the problem. So I'm going to quickly go over some of what or essentially what the LDA looks like. But again, this isn't something that you need to memorize or anything like that. This is more of a reference point for you. So the basis of the LDA is on Bayes' theorem, which is something that you learn in statistics for addressing changes in your system based off of prior knowledge. But we don't need to worry too much about the formal aspects of the theorem. I'll sort of write out what this equation looks like. And so in a logistic regression, we are looking at the probability of a specific outcome k. And we had measured this in terms of these beta coefficients, right? In this that was transformed from a logit equation so that the log of the odds ratio is some kind of linear combination of your explanatory variables. In this case, it's going to look a little bit different. So we're going to have something that looks like this. And here, I think the basis of it is kind of similar, right? You basically have some fraction above as a portion of all the components in the denominator. Okay, and so what are these things that I am describing here? So pi refers to the observed probability of outcome k. And then f of x is a density function of x for an observation from k. And the whole point is here we don't know what fk of x is. And so this density function is essentially referring to if I were to look at the if I were to look at the k outcomes, and then I look at the density function of my explanatory variables given a specific k observation, then, or an observation from a specific k, I should say, then there's this question of what does that shape look like? And so in an LDA, the critical assumption is that fk of x looks normally distributed. So that is something like this. It's just the equation for a normal distribution. Okay. And so there is an equation that is derived from this assumption that allows me to essentially replicate the form of the types of regressions that we're used to looking at. And it looks something like this. So this equation helps us to, it's the discriminant that essentially allows us to estimate the probability of your different outcomes. Again, I don't want to get too deep into the theoretical aspect here. So instead, I think what I'll do is show an application of this in sort of comparison to what we did last time, so that we can see from a practical standpoint how to run this model, how to interpret it, and be able to look at the results compared to a logistic regression. So I'm going to jump over to RStudio. And let's take a look. So this is just a reminder of the stuff that we did from last time. We're still using this data set called car seats from the ISLR package. And we are doing a regression of the shelf location of these baby car seats, regressed on the price of the car seat and the number of sales of those car seats. So this graph here is a visual representation of essentially what we're trying to regress on. And so if you remember from last time, we'll start off with the example of the multinomial logit just to get everyone back on the same page. So this is classification using multinomial logit. Again, this classification is referring to predictions for outcome variables that are discrete. And so these points are the actual points, and then the green, blue, red background are the sort of predicted points by our multinomial logistic regression model. So that is what the MNL will look like. And so now let's take a look at LDA. So this uses a function called LDA. Looks something like this. Let me see. I think it's in the mass package, if I'm not mistaken. Actually, we can take a look really quick, just to make sure. Yeah, so it's mass is one of the bigger R stats packages. It has a lot of useful tools in it for doing statistical analysis. And so if you have that downloaded, that's going to give you access to a lot of different regression methods and tools, in addition to other statistical methods. Okay, and so here we're going to do the same thing. The structure of LDA is pretty much identical to your linear regression. So setting it up should be fairly familiar at this point to all of you. So LDA, regression shelf location on price and sales using the car seats data set. So I can run this. So this is going to be kind of similar to some of the more recent examples that I've given about interpretation. So as we start to stray farther and farther from sort of easy to interpret and known functional forms, your summary results tend to get a little bit harder and harder to interpret. And so, at least in practice, I've really only used this to do predictions. It's saying my connection is unstable. Is everyone still able to hear me? Hopefully. Just let me know if it's starting to distort a lot. Okay. So now what we're going to do, okay, so going back to my point here, I think it's a lot more difficult to do some of these interpretations. We can take a look at the priors, if I recall how to do that. I think it's something like this. No. Okay, I'll put it in the class notes how to look at these specific ones. I don't want to dawdle around too much because I actually haven't. I usually don't look at this, even though you probably should. But the interpretation of these things are definitely a lot less straightforward than in some of the other regression models that we've looked at. But even then, I would say it's not in a similar manner as with logistic regression itself. That those coefficients aren't usually worth looking at besides sort of qualitative reference points compared to other coefficients, and it's kind of the similar case here. I think more of what you'll get out of is thinking about the predictions and how they compare to a multinomial logistic model. And so I can do the same set of predictions where I'm predicting on this new calibrated model using the same sort of range of areas of price and sales boundaries that I want to do. So I'm just going to do the same thing here and see how this model predicts. So those are all the prediction points, and then we're going to do this classification prediction, and we'll see what this looks like. Okay, so I think what you'll see is pretty sort of similar, right? Actually, the slopes here are going to be a little bit different, but this kind of belies what is going on in sort of behind the results. What you'll see is that one of the restrictions of the LDA and of the logistic model is that the sort of separator, if we can think of this in these 3 dimensions, the classifier that separates boundary areas is always sort of linear, right? And this is inherent in the assumption of in the way that these models operate. It's inherent in the assumption of the functional form that everything is sort of a linear combination, even if it's some kind of transformation. There is a plane in which we can project the linearity of the logistic regression or of the LDA, which is what I'm trying to show here. And so these boundaries that are separating the classification or prediction of the LDA model, you can see is being sort of a straight line. And so I think most of the rest of the class we're basically going to try and think about slowly departing from this. And a lot of the models that I'll talk about in upcoming lectures, we're kind of going back to the linear model, specifically looking at continuous response variables. But I did want to take the opportunity now to show one example of a really radically different approach for a non-parametric fit. In other words, we're not assuming anything about the functional form of the model. And so it's not going to be linear, but actually I think that this approach that we're going to talk about is a lot more intuitive than some of the more complex model equations that even now we've been running into, like LDA. Okay, so we'll jump back to the whiteboard, and let's talk about a different classification approach. Again, that is not assuming anything about functional form, and it's definitely not linear. So this is known as K nearest neighbors, or KNN. And maybe some of you folks have heard about this before. So I'm going to write out the formal equation, which looks something like this. The probability of y being j given x at some initial value is equal to 1 divided by k sum of I elements of n, where you have something like this, yi equals j. Okay, so this is kind of complicated, but again, like I was saying, I think that this one is a lot easier to understand qualitatively than some of the previous examples, so don't worry too much about this equation. Okay, so kind of in English, so if I were given a positive integer k and test observation x0, what you want to do is identify the k points closest to x0, which is represented by n0. Okay, and then this estimates the probability for class J as a fraction of points in n0 whose response equals J. And then it classifies x0 to class with largest probability. Okay, what the heck do I mean over here? Let's look at a practical example of this. Let's say I have a couple points like this and a couple points over here. Okay, and let's pick a specific point and classify it. Let's say I'm going to put a point right here. Okay. Does this belong to X, my red X, or my blue circle? At k equals 1, I am going to look at my nearest neighbor, and then whoever my nearest neighbor is, I'm going to classify my my triangle into that group. So let's say that this is my closest neighbor, and so at k equals 1, triangle is X. Okay, what about at k equals 2? Let's suppose that my second nearest neighbor is this guy. At this case, it's actually a tie. It's 50-50. And I believe what it does in this case. Okay, wait, I see a question. Is the triangle an out of sample data? Yeah, exactly. So you've calibrated the, well, it's actually, you don't even calibrate the model. You just give it some existing data, and then you do predictions directly based off of that. Okay. And so actually in this case, it's a 50-50, so it'll choose the one that's closer in the 50-50. So I think it should be a red X. And then at k equals 3, maybe the next closest one is this guy over here, in which case this would be an x, and k equals 4. Maybe the next closest one is this guy, and then it's a tie, and then at k equals 5, let's suppose that that's the closest one. Then now you have 3 blues compared to 2 reds, and now it's going to be a blue circle. Okay, so I see another question. So what's the high-level goal that we're trying to aim for with this procedure, or what is this used for? Yeah, so let's imagine, and actually, hopefully you can even see it from here. This procedure that I'm going through right now is a classification procedure. And I guess the whole point of this is, what if the relationship between these points isn't necessarily a straight line, right? Or it's not areas that can be cordoned off by straight lines. This procedure is analogous to LDA and MNL for predictions, but without assuming anything about its functional form. So I think you'll see a little bit more clearly the strength of the KNN in just a second. And the sort of application of this hopefully should become apparent when we do the example. So let's see.
Hey, Han.
Yeah, go ahead.
Can you clarify why at k equals 2 and k equals 4, it's the x?
Yeah, so for tie breaks, I think it's just for tie breaks, it's going to go with the one that it was before. I think I'm actually realizing I'm a little hazy on this, but the reason why I think it would go on the one before is because that would indicate that that's the closer one, right? Because so at k equals 2, I've entered into a tie break, but the previous one I was clearly in the red X, which means that the red X was closer than the blue circle. So when you have a tie break, it's going to look at the previous K and see what that is.
Okay.
Yeah.
Thank you.
Okay. So everything that I'm showing here is essentially describing the more formal process that I wrote here. It's pretty straightforward, right? It's really just a matter of for any point, what are I'm going to classify it based off of the numbers, the number of Ks that I have. Okay, so let me ask a question. Okay, wait, I see a question here. Is the distance magnitude not matter in the classification, just the distance order? Yeah, so the magnitude and order play a role, right? Because what the model takes into account is the relative magnitude, right? Because if for example, this looks something like 1 and 1.1, 1.2, 1.3, 1.3, 1.4. It cares about the size of it for which one it's going to classify, as well as the order as you go from closer to farther. So it's going to choose this one first, and then it's going to choose this one, and then it's going to choose this one, and then I guess these two, and then this one, right, in order. So if I have k equals 1, then classifies as nearest. What happens as k approaches infinity? What would let's say my k in this particular example is equal to 100. What would my triangle be classified as? Can anyone make a prediction?
Blue, because there's more blue points.
Yeah, exactly. And so as k approaches infinity, classify as most prevalent class, right? And so if my k were infinity, then no matter where I put my triangle, even if I'm in the middle of all my red pieces, it's always going to be blue, because there are more blue points than there are red points, right? Because you're looking at basically all the neighbors and classifying it. Okay, and so how do we choose k? Can anyone venture a guess as to how you might select k in a robust manner? I'll give you a hint. We've been doing this for lots of different models now. So cross-validation, right? And so if you have a testing set, you can compare how that actual predicted data is going to look compared to the true data. And you can vary your k parameter in the same way as you might vary, your tuning parameter in Ridge and Lasso, and figure out what k gives you the most accurate observations. Okay, so I see a question. Is it possible to put a limit to range of neighbors for specific points? No, I don't. Well, you could, and you could do it manually, but I don't think this is something that you would want to do. It doesn't, I guess it doesn't make much sense to do. I don't think it would make much sense to do this, because if you let the k nearest neighbors operate in the way that it's intended, I think what you're worried about is that specific boundaries and ranges of points to other points may not make sense as you expand, but that's really controllable by basically setting your k to a good value. So I think I kind of see where you're getting at here, but I think that the KNN approach is robust enough to be able to deal with those kind of issues on its own. So I want to jump back to RStudio. Oh wait, okay, so I see another question. Is K nearest neighbor the same as K means clustering? No, it is not. It is related, and you can conceptually see how, hopefully if you're familiar with K-means and the procedure for estimating K-means, hopefully you can see how it is somewhat related, right? Because it's taking sort of magnitudes of distances, but it's definitely not the same. And yeah, we'll actually talk. We'll actually get to K-means at some point later in the course, but they're not the same. Yeah, I'll leave it at that for now. So okay, so I see a question. So once the triangle is classified, is the value of the triangle assigned to the nearest neighbor? Yeah, that's exactly right. Well, that is what the classification is. It's assigning a value for my black triangle. So I'm trying to figure out, should my black triangle be a red X or a blue circle? And with this algorithm, we have a means of classifying it into one of these two things. Great. So let's jump back over here. So now we'll do an example for KNN. Okay, so there's no like model here, right? It's just this algorithm. So we're just going to do the prediction straight off the bat. And that uses an equation, or sorry, a function called KNN, which, let me see what package this is from. Oops, not test, help. Okay, this is from the package called class. So it needs a training set and a testing set. So the training set is the data that I'm going to use for my KNN, and then the testing set is what I want to predict on. And so we're going to use our original data set for training. And then we're going to use this test set that I've come up with, which is basically all of this area, right? I'm going to test every single point in here, and then we'll see what it says. If I wanted to do cross-validation, then I would, so in this test set, it's just totally arbitrary. It's just a whole smattering of points across this area. But if I wanted to do cross-validation, I would take a subset, right, out of this data. So this is the same type of cross-validation that we've been talking about. We could do a k-fold where you randomly select some amount out of here and you put it into the test set. And so you can compare the prediction against data that you actually have, and then you'd effectively be doing out of sample prediction. The thing that we are interested in is the shelf location. And then we want to we want to specify our k nearest neighbors. So in this case, I am going to say, actually, why don't we start with k equals 1, see what that gets us. And then we'll just put it into a ggplot. I see I have an L equals 0 here. I'm actually don't quite remember what that is. Minimum vote for definite decision, otherwise doubt. So more precisely, less than k minus 1 dissenting votes are allowed, even if k is increased by ties. To be honest, I don't remember exactly what that means. I'll look into that and I will include that in the notes.
That description was super helpful.
Yeah, I know, right? What does L do? I will make sure that I understand what's going on there. Okay. We gotta do this. Cool. Okay. So what is going on here? This is at k equals 1. Okay. And that means I'm going to just pick an arbitrary point anywhere in this area, and whatever point that it's closest to is going to be that color. So if I'm right here, the closest point is this point, and so it's blue. If I'm right here, the closest point is red, and so it's going to make that red. But if I'm right here, the closest point is blue again. Note that that this isn't normalized in any way. So it's thinking of distances relative to you know, these magnitude of sizes. And so if you did want to normalize it, you'd have to put everything into the same scale. And so that can be one particularly difficult part of this, because it ends up weighting things that are closer together just by terms of its scale for whatever variable that you're looking at. So that's one thing to keep in mind with this sort of model. But let's jump up and see what happens, right? And actually before I do that, I'll also mention that this boundary, the boundaries for all of these nearest neighbors is like very not linear, right? So you can see hopefully immediately a pretty big difference between the KNN and the LDA and MNL. And actually, let me just make this equivalent. We'll do size equals 3. Oops. Okay, so now we're going to jump up to, you're going to look at the 3 closest neighbors instead of the 1 closest neighbor. And here you can start to see some differences between this one and the last one. We'll continue jumping up to see the effect. So this is 5 nearest neighbors. Still pretty close, although some of the mixing is gone. And then let's go, let's say 10 nearest neighbors. And you start to get more sort of solidified boundaries. And as you increase your K, note that one of the things that your solution will converge to is to the one that has basically more points. Okay, and so this is what I was talking about as you approach infinity. Let's go ahead and put, how many data points are in here? 400. So let's go ahead and put 400. Everything becomes red. And why is that? Well, if we look at the data, wait a minute, that doesn't seem right. Why did that happen? Hang on. So what I would have expected is actually it should be blue for medium, because you're essentially going to look at every single point in here and all the points, and so whatever one has the most points, it should be that color. Yes, yeah, that's right. Okay, I see. Does it have to do with scaling? Actually, in this case, it shouldn't, right? Because you still have to look at your nearest neighbors. Well, that was an anticlimactic punchline. Let's see. I have no idea why this is happening. Okay, one sec. 400 observations. Okay, wait, I see a question. So when you select K, are you selecting a specific point? So K looks at the 100th point in the data set. No, so K is looking at the, essentially it's telling you to look at the K nearest neighbors. So it's going to say, I'm going to look at the 400 nearest neighbors to this guy. So blue, green, 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 then blue, blue, and then it's going to look all the way until you've hit 400. And it should be blue because there are more blue points than anything else. So I guess I'm a little bit confused as to why this is happening. Okay, I guess I have to look into this and figure out why this is the case. But
I don't know if this is why, but wouldn't it be 401? Because couldn't the 400th data point still be red?
Yeah,
Like,
it could be, but like it's not like there's like 201 mediums and 200 bads, right? It's like very clearly in the medium one. So I don't think that's the case. I mean, I could I could try it, but I don't think that's gonna do. Yeah, it's gonna exceed the number of patterns, so that's not even gonna work. I wonder if it has something to do with being right on the edge.
Is the red background referring to medium? I mean, it looks like on the legend it says.
Oh my God! Oh, you're right. Oh, okay. Thank God. Okay. Yes, I know. Okay, I know what's happening. It's the coloring scheme. You're right. Oh, phew. I thought I was going absolutely crazy for a second. Okay. So yeah. So what ends up happening is that when you run a plot, it's going to, the default color is red for the first one, and then red and green, and then red, green, blue. And because there's only one item, it just colors it as red. I didn't specify that it should have been the right color. So this is actually what we expect. Sorry, this should be blue, but because it's missing the other two, it just went to the first color value, which is red. Okay, thank God the KNN function works. Yeah, so this is solidly red. If we jump back down, I think it'll do. It might still be all red, yeah. So still, when you look, because there's so many more blue points, even at something like this, it's quite still has only one outcome. But I think if we do 20, yeah, there we go. Yeah. And so the blue portion, or I should say the medium shelf location, is going to grow and grow and grow because it has the most points in it. Okay. So you can, as we go through all these different classification methods, if you are ever doing any sort of classification approach, I think it's always a good idea to, and this speaks more generally to thinking about non-parametric approaches. In some fields, such as like choice modeling, we typify our approach, or we standardize our approach, and most people in the field will do something like, you just do like a logistic regression or nested logit, or mixed logit, or however, and you are really those that are really fundamental in the field will be really careful about thinking about assumptions that are inherent with the model to make sure that everything is like statistically robust and so on and so forth. But I think that very few people take the time to think about whether or not the functional form of the model that I'm choosing is appropriate for the data that I'm fitting to. And so as you do work in that domain, I think it's always, always, always worth checking to see if the functional form makes sense. In other words, do I think that in this model where I have this line, is that really how the data is sort of structured to fall into these linear boundary separators? Or does it look more like, I don't know, something like this, where it's not linear? And so it's not always the case, or oftentimes, it isn't linear, but it's close enough where you're okay with it. But in some instances where it's very clearly not linear, you do need to be wary and cautious about whether it makes sense to do the sort of semi-parametric approaches that you're doing with the logistic regression or with an LDA. All right, we are a little more than halfway through, so let's take a quick break till 11:09, and then we'll pick up again on a new topic.
Alan, can I ask a question about the homework?
Yes, go ahead.
Yeah, just on the second problem, I understand the theory of the backwards as in you take all coefficient and narrow it down. I'm just kind of confused on where in the code to change it. I'm wondering if you could give me some pointers.
Yeah, let's see. So it's analogous to the front. Yeah, it's analogous to stepping forward, except instead of adding variables into your sort of best model hold or whatever it's called, you are taking them away. Yeah, so if you think about, let's see, if you think about having, say, a whole bunch of variables in the model, as you step back, you include all of the variables, and then you take them, like in each interior step in the interior for loop, you're essentially taking one point away at a time. And so if the variables are called 1 through 10, then I would take 10 out and run 1 through 9, and then I would take 9 out and run 1 through 8 and 10. Then I would take 8 out and run 1 through 7 and 9 and 10, and so on and so forth, until you figure out your best one, right? And then you go to once you do all of those steps, you move to the next interior step, which is taking that best model and then removing them. And so I guess everything that you're doing is analogous to step forward, except that you are removing variables instead of adding variables. Does that make sense?
Yeah.
Yeah,
So kind of in that second orbit.
Yeah, and so you're removing them instead of adding them, and instead of starting with one variable, you start with 10 variables. So in step forward, you go from one variable to all 10, and then in step backwards, you go from all 10 down to 1.
Okay. Yeah, for some reason I was having a hard time. Every time I would try to do that, it would still start with 1, but I think that's just a coding problem.
Yeah. So make sure that at the first step that you have all the variables included, and then you take them away one at a time.
Okay.
Alan, could I ask a clarification on that as well?
Yeah, go ahead.
Yeah, so you said that you identify the best model at each step, and then that model will have one missing variable, and then you repeat again, removing another variable from that best model. But so what you're not doing though is you're not identifying the worst model at each step, and whatever model that is, removing that variable.
Okay, let me think about what I was.
Yes.
Yeah.
So like, do you need to at each step when you're iterating through, like you remove variable 1, then you remove variable 2, then 3. Your goal isn't to identify the worst model, and then. Oh yeah, okay. I think that would make sense. Yeah, okay. I think I answered my own question maybe.
Yeah. So, I see where I definitely see where the confusion is, because it's a little weird to wrap your head around, right? But like the best model that omits the last variable is like, if you think about it going forwards, right? That's how it would work. It would pick the best one out of those, and as you step back, like within the group, you're getting the best one every time. So it isn't I can see why it would be confusing, where you would think that it's like the worst variable and you get rid of that variable, but actually it's like you're picking the best model within each step, and then going backwards, so that it'll be exactly equivalent to going forwards.
Yeah, that makes sense. Okay, I need to redo that then.
Yeah.
So at some point, you'll find that the best model is keeping all of them in, or like a certain point.
Within each one, yeah, like your R squared is definitely going to be the highest at the first step, your internal R squared, because it has the most variables. But when you do the cross comparison of all the models that you've identified for like one variable or two variables or three variables and so on, the AIC, BIC, and adjusted R squared are meant to account for the number of variables as well. So it should be able to tell you the best overall.
And
yeah, go ahead.
A clarifying thing, the reason we use the R squared internally is because there's no bias associated with the amount of variables, because they'd all have the same amount of variables.
Yep,
within
exactly.
An intermediate step. Okay.
Yep, that's right. R squared is just one metric that you don't have to use R squared, but I think it's the most commonly used one. Yeah. Okay, I see a question. Does the function have to apply to any data set or just the hitters? I think I asked for it to be generic, right? Or is that? No. For problem 2, yeah, the generic one is the cross-validation one, but for problem 2, yeah, it can be specific just to the hitters. That's okay.
Excuse me, I also have a question about the comparison between forward and backward methods.
Mm-hmm.
Do we need to necessarily get the same results and models from both methods? For instance, if I get something with 5 parameters from backward, do I need to get the same thing from forward with the 5 parameters model?
No. Yeah, that's a really good conceptual idea. It's very often the case that you do get the same answer, but you don't necessarily need to arrive at the same one, right? And think about why that is. The way in which you're excluding variables is different, and you may have some combination of variables that are like slightly better at let's say so for example, I'll do a really simple example. Say you have 3 variables. You have x1, x2, x3. Say you have x1 is the best single variable, but if you have 2 variables, say x2, x3 is the best combination of 2 variables. If you were moving forwards, right, you would exclude that combination from ever happening in a step forward, right? Because I have excluded, or I have to include x1 in my next step because x1 is the best one in the first stage. But if I were going backwards, maybe I exclude x1 in that second stage. So then you would arrive at a set of variables in your backward selection that you could never get in your forward selection, and that is definitely possible to happen. So yeah, they don't have to be equal, the results from a step forward and a step backwards.
Okay, thanks. It makes sense. And is there any discussion over which one is better?
No, usually people run it both ways just to make sure that it's close enough. Or they'll run it both ways and then do the higher adjusted R squared for comparison of the best step forward and the best step backward model. Remember, this whole idea of doing step forward, step backwards, it's about pruning the amount of models that we have to make. They're not empirically going to be the best models, and there's no reason that they would be, right? It's just a technique in which, you know, if I have, oops, let me, I was trying to draw on the screen. If I have x1, x2, all the way to xk, there are, how many combinations of ways could I do this? It would be 2 to the k, right?
Yes.
So the whole reason why we do step forward is and step backwards is to reduce this to just k number of models. And it's not such a huge deal to say, I'll run it step forwards and there's k number of models, and I'll run it step backwards and there's k approximately k. I know it's not exactly k. And if you do it both ways, then that's just 2k, which is still much smaller than this. So yeah, people will often do it both ways and pick the best one out of those two.
Okay, thank you.
Mm-hmm. Okay. Let's go ahead and talk about the next topic that I was discussing at the beginning of class, which is moving beyond linearity. So beyond. Okay. As we move away from linear models, we often lose interpretability, but we gain predictive power and flexibility in fitting models. Okay, and so what we're going to do here is I'm going to give a quick preview of the stuff that we're going to be talking about over the next couple classes. And we're going to go, essentially what we're going to be doing now is step by step sort of layering in more and more complexity into our sort of departure from linear models. So the first thing that we're going to look at is simply polynomial regression. And then we're going to look at step functions. So hopefully we'll have time to look at both of these today. And so these are, some may even still consider this to be like solidly in the realm of linear regressions. And the reason for that is we are essentially doing or using what's called basis functions. And so this is a family of functions or transformations that can be applied to a variable. And we'll obviously, we're going to show what those transformations look like in just a bit. And then we're going to start looking into combinations of these basis functions to create what are known as splines. So we're going to look at regression splines, we'll look at smoothing splines, then we'll start to get into local regression, which shares some similar ideas as the KNN that we looked at. And then lastly, we'll look at general additive models. Okay. So in a polynomial case, we are going to essentially just transform our regression equation. So yi equals beta 0 plus beta 1 xi plus my error term. And essentially what we're going to be doing is something like this. Beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed, and so on and so forth. Beta d xi d plus my epsilon. Okay, and so I think I actually showed an example of this in an earlier lecture. And in this case, this can be overly flexible and take strange shapes near boundaries of X. In other words, I think that this is not super complicated. The sort of fundamental workings of how you would go about doing this is pretty straightforward, right? This second equation here isn't really any different from the linear regressions that we've been running. But if I were to try and figure out what the best polynomial is here, can anyone tell me how I would choose my value of d? I'll give you a hint. It's the same thing we've been talking about for choosing parameters for most of the different model fits.
Cross-validation.
Yay, cross-validation. Yeah, exactly. So we choose our D via cross-validation. This is why it's a really powerful tool. The cross-validation is essentially saying, how do I make sure that my model is the best one? Well, it's the one that can predict most accurately out of sample observations. Okay. I'm going to go ahead and talk about piecewise regression, and we'll just show both examples sort of simultaneously in R. But so we'll go ahead and talk about this first. This is also known as a segmented regression. So as I go through these two examples in particular, I will say that these are not like these approaches are not very common to do any sort of real analysis on. The question of like, oh, when does it make sense to take this approach? Well, really, it would only really make sense to do a polynomial regression if the functional form of your regression were literally some kind of linear combination of polynomial components of your data, which is kind of rare or fairly unusual. I've never seen it in my sort of practice of doing data analysis. And so why are we doing this? Well, this is kind of building up a base for venturing into non-parametric models that people do actually use very commonly. And so we kind of need this background to understand the next sort of steps. So when I talk about these sort of things, whereas these are kind of theoretical in nature and not used very often, these guys are used for lots of different types of prediction, and they're very sort of powerful models, and they build directly off of what we're learning about here. So don't worry too much about the application of what I'm talking about, but hopefully you'll understand. I think that these models are kind of simple enough that hopefully you guys should be able to grasp and understand, and it'll be important to have that understanding as we move on to the next steps. So polynomial, just again, linear combinations of polynomial orders of your existing data. Piecewise regression is also, I think, pretty straightforward. So this is in our regular model, and this just kind of gets split up where now you have two portions. Actually, maybe I'll use a different parameter here just so it's not confusing. So, okay, so BP stands for breakpoint. All this is maybe you have something like this. Maybe your data looks something like this, and then maybe it looks something like this. And suppose I choose a breakpoint right here. Then all you're doing is, say, fitting regression line like that. So that's called piecewise regression or segmented regression, and it's going to create a breakpoint BP to separate the data, and then you essentially calibrate your regression individually, and you get these two regression lines that look something like this. Again, the question of, okay, when do I use this? Well, you would really only, the place that it would make the most sense to use this is if you literally had a breakpoint in your data and they were linear on both sides in different ways, right? That's essentially when it would make, that's when the functional form would match what this model is doing. Yeah, can you have multiple breakpoints? Yeah, definitely you can. You could segment this in as many ways as you want. Yeah, so let's see. Okay, another comment, also applicable for dummy variables. Yeah, well, okay, let's see. I don't think it would be, it's not quite the same as dummy variables, I think, because a dummy variable is like you're essentially, well, okay. I can see why or how that comes up, but a dummy variable would be explicitly like looking at one set of data points. This still includes both of them, and the line isn't a single line that applies across. I think the big difference is that the line applies across the full continuity of a single variable, as opposed to separating them and then having them different lines. Yeah, I guess theoretically the concept is pretty similar, because you're essentially creating different lines for different different points. I wonder if that's just kind of like a what's it called, like a nuance of the way we call it, because I see why in principle it's pretty similar. But okay, I guess as long as you understand the distinction between what a piecewise regression is doing and what you're doing with fitting a dummy variable, I guess it doesn't matter so much, because really what we're going to want to do with this is going to be something different at the end of the day. Okay, so why don't we jump into R and we'll show how to do this. And again, I will sort of say that it's not so often that we run these sorts of models in practice. But again, it's good to know about, and it'll definitely help with understanding what splines are, and because they really are building off of what we're learning right now. Okay, so we're going to depart from linear models, and I'm going to create a function. This is I know we haven't done this in a little while, but if you'll recall in earlier lectures, I'm essentially creating my own sort of function based off of random numbers. So I'm going to have x is randomly drawing 1,000 points from between 0 to 5. I'm going to create a deviation. This is just a normal distribution. And in this case, we used to do this thing where we said y is equal to 0.5x plus deviation or something like that. A linear relationship between x and y. And what I'm going to do here is actually a little more complicated. I'm going to create a nonlinear relationship between x and y. So y is a function of sine x times cosine 10 times x plus 0.5 times x plus a deviation. So I'm going to run this and then I'll plot it so that we can see what this function looks like. So this is a function relationship. This is a relationship between x and y that's really clearly not linear, right? And so what I'm going to do is I'm first going to fit it to a linear model and see how we do, and we'll plot it and look at what this looks like. And it's kind of what you expect, right? So the line is just going to go right through all of the points, kind of right in the middle. And that's what the linear model is describing. If you look at the data, though, you hopefully will be able to see that it's not necessarily a fit that makes a whole lot of sense. And in fact, if I were to look at the residuals, okay, I want to plot, let's see, x is equal to predict linear model and y is equal to resid of my linear model. Yeah, so hopefully here you can see, so residuals of linear model. This if you ever see a residual plot that looks like this should be ringing all kinds of warning bells, right? Because this definitely looks like there's a pattern. It doesn't look like it's randomly distributed noise. And so what that tells me is that my linear model is definitely not a good fit for whatever it is that I'm trying to fit on. And so what we can do is run a polynomial regression, and I can go ahead and do that. So this is a built-in function that lets you do all the polynomial orders of x. And so if I say poly x5, that's going to, actually, I wonder if I could just do it explicitly. X comma, let's say 3. Yeah, so it creates this special sort of data structure. And if I look at this is going to be the actual value, I believe. Let me see. No, that's not going to be the actual value. Okay. I guess what I'll say is this: if I run this model, I guess the interpretation is a little bit easier if we just look at the model directly. It will tell you what the coefficient relative to x, and then x squared and x cubed and x fourth and x fifth and so on and so forth. And what I can do is take each of these models and predict based off of these. So let's take a quick look here. Okay, so for each of these polynomial models, I'm going to take that model, so the one with 5, 10, 15, and 25 orders of polynomials. I'm going to predict across the full range of data here, and then I'm going to plot it and see what those fits look like. So this is the equivalent of that red line. So this is the equivalent of this plot right here. So where the red line is linear, we're going to look at what it looks like for all of these weird polynomial fits. Okay, I'm going to plot these one at a time. Oops. I have to run these, which means I have to run all these. Okay. Oops. So here, this is the red line is our initial line, and then our blue line is with polynomial order 5. Now let's take a look at the next blue line, which is going to be polynomial order 10. And you can start to see a little bit more wiggling, right? And especially at the ends here is when you typically start to see a lot more crazy things happen. Let's go with 15. Okay, and then you start to see even more wiggling. And now let's try 25. Okay, let me do line width equals 3. So we can see, yeah, there we go. So as you do more and more of these, you'll end up getting sort of closer and closer to the data, right? And of course, you may be worried about, and before I talk about that, what I was saying before about boundary conditions. With polynomials, you tend to get this sort of thing here. If you look right on the left-hand side, where things start to get really crazy at the ends. You don't see it so much in this case, but that's one of the features of polynomial regressions, is that it becomes very unstable at the end. Yeah, and so as I increase more and more, you can imagine that it starts to get more and closer and closer fit, until at some point you start to wander into the territory of overfitting, right? Where you are increasing the error component that's contributed by variance relative to bias, and then you start going up that that U-shaped error curve that we've been showing for the bias versus variance trade-off, right? And so
I didn't get that. Could you try again?
Whoa. Sorry. And so as you, hang on, I think my Siri just freaked out. Okay, sorry. So as we increase the number of the orders of our polynomials in the model, you'll start to get things like overfitting, right? And so the choice of how many orders that we go to can be selected via cross-validation. Okay, wait, I see a question. So when using polynomial, we will start from x to x to the n without skipping any order between 0 and n. Yeah, so I think that's done kind of more from a practical perspective, because like if I were to go to x to the n, you run into the same issue, right? Where if you want to look, if I want to look at x squared, x cubed, ... x to the n, if you want to look at different combinations of these variables, you're going to run into that same issue where you have to test 2 to the n number of models. And so we just tack them on at the end. And then if they don't happen to be really impactful, it doesn't really hurt the model at all. I think at this point, you're sort of solidly in the, like, I don't care about the interpretation, I mainly care about the prediction. So throwing in more variables isn't that problematic. Let's try, so I suspect that this isn't gonna work, but let's try something like this and see if we can force the model to do some overfitting. Degree must be less than the number of unique points. Okay, we definitely have less, or we definitely have more than 100, but I think I've run into this issue before. I'm not exactly sure why this happens. It must be number. Yeah, I guess we're not going to get too much bigger. If I were to, I think it has to do with the way that poly fits. It's actually something to do with the function poly. If I were to manually do it, I could do a fitting on hundreds of orders. And what you end up seeing is this kind of behavior throughout, where it starts to get like really sort of squiggly. And then that's when you start worrying about overfitting. But yeah, I would leave it at saying that in the similar vein as we've been doing with selecting parameters such as the ridge and lasso for the tuning parameter, and as the k for the k and n, the way that you select the number of polynomials is via cross-validation. Okay, so let's now take a look at piecewise linear regression model example. So this uses a regression function called segmented. Yes. I don't have it installed, so I'll install it real quickly. I'm getting flashbacks to last year, actually, because we were in a room that didn't have internet and I didn't have it installed. And so I couldn't actually show this example, but I do have internet, obviously. So now I can show it. So we are going to do a piecewise or segmented model. So I'm going to run this model called segmented. And it's got a couple unique options here, which I'm going to show what these are in a second. We can look over at the help function. Okay, so let's go on over to this. So you'll note that there are a couple unique function inputs here. The first of which is seg.z. So this is the segmented variable. So when I showed the example with the breakpoint, where we have something like this, this was kind of easy to demonstrate, right? Because you are just operating with a breakpoint in one dimension. But you can imagine that if I have multiple variables, I might want to do breakpoints at some of them and maybe not all of them. And so this this option is the thing that lets me choose which variables that I'm going to do my breakpoints on. So the PSI input is just telling you where you want the breakpoints to be located. And so you can explicitly specify this, or you can calibrate both the number and location of the breakpoints, although it may be a little bit difficult to do this manually through cross-validation. So in this case, I've just asked it to do a separate linear fit at every, from 0.1 to 4.9, every 0.05. So it's going to have approximately, how many regressions is that going to be? So 100. So there should be about 100 different lines that I'm separating my model into. And then I'm going to so after I run this model, starting PSI out of range. One second. I think I know why this is happening. A lot of bugs today. So min of x should be in range, but I'll increase this a little bit. Say 0.2. Okay. And let's take a look at this. So here's our original model, and then I'm going to do forest green, and I'm going to make it a little bit wider, equals 2. Okay, so this is the piecewise prediction if I break it up many, many times. Whoa, okay, hang on. Not what I expected. I think I have a typo somewhere then. Okay, I think there's some, let me just re-estimate my x. No, okay, starting PSI out of range. Let's see what happens if I go really far up here. I just tested this too. No breakpoint estimated. Is the linear model correct? Yeah. Okay, this is apparently not working today. Summary piecewise model. Yeah, it's just, for some reason, it's still estimating as a linear model. Give me one quick moment. This is the last thing we're doing today anyways, so bear with me. Okay, maybe I can try NPSI. And that's going to choose the breakpoints for me. This is not quite what I intended, but hopefully it should give similar results. Whoa, there's no starting point though. Okay, well, it appears that I might not be able to get this to work right now. Yeah, so instead of flailing around in front of everyone, I will see if I can get this to work again on my own, and then we'll just start next lecture, and I'll show what this looks like. It shouldn't take too long. I mean, essentially what it's going to look like is if I were to get it to work, we could have it look something like the polynomial example, where you have enough lines where it kind of sketches out this sort of exact shape. And so it's going to be essentially a couple different methods of getting to fit to this weird sort of shape of data. And then what we're going to do with splines is connect both the piecewise and the polynomial regressions together in a certain way that will allow us to more sort of flexibly be able to combine the sort of strengths and weaknesses of the segmented and polynomial models together. Yeah, so sorry this didn't work. I'll make sure to get it all working before next class, and we'll be able to see what the plot looks like. Okay, and so like I said, that was the last thing that we're doing today anyways. So we'll end here, and then yeah, we'll pick up hopefully with a working version of this segmented model next time. In the meantime, yeah, just let me know if you have any questions. Otherwise, I will see you guys next Tuesday.
Hey, Alan, for the piecewise model, you might